So now we're going to move into the concept of multiple linear regression. And so this is where you can now have more than one predictor variable to predict what your outcome variable is going to be. So if we look at what the multiple linear regression model looks like, you see that we have our beta naught plus beta 1 x1 plus beta 2 x2 all the way to beta q xq plus our error value, where y is our dependent variable, x1, 2, and however many we have will be our independent predictor variables, and our beta weights are our population parameters, with e being our error term, talking about the random variability in y that cannot be explained through the linear effect of however many independent variables we have. And so when we look at this, the way we interpret the slope coefficient for our beta weights is that it represents the change in the mean value of the dependent variable that corresponds to 1 unit increase in the independent variable, holding all the values of all the other independent variables in the model constant. And the multiple regression equation that describes how the mean value of y is related to each of our predictor variables is e of y of x1 to however many you have is equal to beta naught plus beta 1 x1 plus beta 2 x2 all the way up to beta q xq. So remember, we have our estimated multiple regression equation where we have y hat is equal to b naught plus b1 and so forth, where our b values are going to be our point estimates from our sample of our population values of beta 1, 2, 3, and so forth. Y hat, again, is our estimated value of our dependent variable. And so we can use the least squares method to develop that estimated multiple linear regression equation, finding the combination of our different b values that will satisfy our expectation to minimize the sum of squares. And so we're going to use our sample data to provide our values of b0, 1, 2, 3, and however many, so that we can minimize the sum of our squared residuals. And so the estimation process for the multiple regression is going to be shown here. The estimated values for the dependent variable y are computed by substituting the values of the independent variables x1, x2, however many you have, into the estimated multiple regression equation. And then you can use computer software packages to obtain the estimated regression equation and then determine the regression coefficients of b naught, b1, 2, and so forth. And so when we were looking at simple linear regression, we were looking at lowercase r squared. Now with multiple linear regression, we're looking at capital R squared. And it's calculated to be an indication of the proportion of the variance in the dependent variable that's explained by the combination of the predictor variables that we have. But the catch is when you have multiple linear regression, the more predictors you add, intuitively, you should expect that you will have more of your variance explained. However, there's a penalty that comes with it, and so we have this thing called adjusted R squared, where we take into account the number of terms in the model, K, and the number of observations in our sample, N. And so when we look at certain evaluations, we look at the difference between our R squared and our adjusted R squared. And oftentimes we can see that R squared and the adjusted R squared will improve just a little bit, but not a whole lot, just a little bit as we add more predictor variables. So let's go back to our Butler Trucking Company example. In our previous discussions, we calculated that the simple linear regression equation was going to be 1.2739 plus 0.0678 xi. Okay, so we also found that our R squared, our coefficient of determination, was 66.41, meaning that 66.41% of the miles traveled explained explained 66.41% of the variability in our travel time. Therefore, we end up with about 34% of our variation in our travel time that's not accounted for. And so the managers of this company in this scenario are saying, okay, 34% is still quite a bit unexplained. What's going on? And so what we're going to do is we're going to now include the variable of the number of deliveries on each of the routes. And one thing to keep in mind is when you add more predictor variables, you need to have a larger sample size. And so we're going to go ahead and use all 300 driving assignments for this company just to make sure that we are capturing as much as we can. And so we're going to use our estimated multiple linear regression equation with two independent variables. So we have our y hat plus beta naught, which is our y-intercept, plus b1 x1, which is going to be our slope for our x1 variable, and then b2, which is our slope for our x2 variable. And then we can calculate the sum of squares total, sum of squares regression, sum of squares error, and the r squared using the formula that we talked about earlier. Or we can use a statistical software package to get this kind of output here. And so here's an output from SAS shown on the screen. Remember that the label for the independent variables is going to be miles, and the label for our independent variable will be deliveries. And so you can see here that our estimated regression equation is going to be 0.1273 plus 0.0672x1 plus 0.69x2. And so these values are coming directly out of the parameter estimates table that's provided to you in the output of from your statistical package. And so we also see now our r squared has gone up to 0.8173. So now that means that we have about 82% of our variance is explained by the combination of miles and deliveries. And if you look at the adjusted r squared is still about 82%. So really either one of these values would be sufficient for that discussion. But note that if you start adding more predictor variables, you're going to see a bigger change between your r squared and your adjusted r squared. And in those cases, you would want to use the adjusted r squared for when you look at how well the combination of your predictor variables explain the variance in your outcome variable. Another thing on this output that we want to look at is this is our sum of squared regression. So in our ANOVA table, this is called the model line, but this is really your sum of squares regression. And then here we have our sum of squares error, sometimes called sum of squares residual, depending on the software package that you're using. And then we have our sum of squares total. Then you can also look at your mean squares, which is your sum of squares divided by your degrees of freedom regression or model. And then you have your mean squares error, which would be also sometimes called your MS residual. So that's going to take your sum of squares error divided by your degrees of freedom error. And then you get your F value by taking your mean squared model divided by your mean squared error, just as you've done before with a previous ANOVA table. And then when we look at our F table, we can see that this value has a p-value of less than 0.05, which is good. When we're doing a regression equation, we do want to make sure that our F statistic is lower than, the p-value for our F statistic is lower than our alpha 0.05. And remember, typically you do use 0.05 as your point of reference. And then the other thing we want to look at is our mean squared error. When we take the square root of that, we get our RMSE is what we call it. And this is your standard error value. And the next thing we have is our R squared, which we looked at previously, which is the amount of variance explained. And then we get that by looking at how much of our model explains the total amount of sum of squares that we're looking at. And then our adjusted R squared is the variance explained that's adjusted for based on our number of groups and our number of observations. And so we need to keep in mind the number of observations that we have and our degrees of freedom from our model. And then we can do the hypothesis testing um, for our individual slope values as well. Because remember, we have you're testing the hypothesis that the different slopes are not zero. And so remember, you take your t-value and you can find the associated p-value that goes with it. And that will give you the p-value of your t-statistic at that particular number of degrees of freedom. And so here we see that both our miles and our deliveries are statistically significant at the appropriate level of degrees of freedom. So that's going to tell us that they are not zero slopes and they are valuable in predicting our outcome variable in our model. And so we can make a graph of a multiple regression analysis if we have two independent variables. If we have more than two, it becomes a little bit more complicated. But with two independent variables, x1 and x2, we can generate a predictive value for y for every combination of those values of x1 and x2. Therefore, instead of a regression line, we're now creating a pane in three-dimensional space. And so this figure here is going to provide a graph of the estimated regression pane for our Butler Trucking Company example and shows the 7th driving assignment in the data. And so as the plane slopes upward to larger values of total travel time, which is our y value, as either the number of miles traveled, x1, or the number of deliveries, x2, increases. We also see that the residual for a driving assignment when x1 equals x star 1 and x2 equals x star 2 is the difference between the actual y value and the expected value of y when x1 equals x1 star and x2 equals x2 star, or when e of y of x1 star and x2 star. The observed values are going to lie above the regression plane, indicating that the regression model would underestimate the expected driving time for our 7th driving assignment.